Today, I'll be discussing HAC-T and fast search for similarity and security. I'm Jonathan Oliver, and I'll be presenting this material with Makit Ali. Let's look at hashes in security. Typically, cryptographic hashes such as SHA-256 are used. They're very convenient for sharing and processing malware samples, various security elements. Similarity digests retain much of this convenience, but there's a key difference. Cryptographic hashes, if you change a single byte in the underlying file, will completely change, whereas with similarity digests, only a small number of the bytes of the hash change, and hence you can measure the distance or similarity of two files or other elements that you might consider processing. So for example, memory dumps, sandbox logs, there's a whole variety of security elements you might choose to apply similarity distances to. So the types of applications we might consider is looking at goodware and malware files, automatically forming groups, as shown in this diagram, automatic processing of them. So it's very useful to be able to automatically put together and find that files which are related, perhaps members of the same malware family, are a close distance together, and if you can automatically put them together when you get a new sample. Let's do a quick introduction to TLSH. TLSH is one of the open source similarity digests. So let's look at two versions of Chrome.exe. So we've got two files. Their SHA-256 we see is completely different. So their hashes have no bytes in similarity. When we look at the TLSH hashes, we find that there's a lot of commonality between the two hashes. We highlight in green the differences. In addition, we can take those two hashes and we can measure the distance between them. So it's a near Hamming distance that gives that distance of 9 between these two hashes. In addition, we can achieve this by collecting these hashes from two different points. So there might be two different people in the world, each of which have submitted these hashes to some joint repository, and we can measure, yep, those files are similar. Previous work in this area includes 3 similarity digests that have all been open sourced: SSD, SDHash, and TLSH. I provide the key references. There's been 2 recent studies, a CodaSpy 2018 and Moving Target Defense 2018, that looked at these and other similarity measures for security applications. They determined that TLSH and SDHash were more accurate than SSD. They identified that SDHash and TLSH were suitable for security applications. TLSH has been made a part of the STIX 2.1 standard. So the criteria used for evaluating these measures, well, first of all, we want them to be a general purpose tool. We want them to be able to apply to all different file types: HTML, JavaScript, .executable files, ELF binaries, any particular file or binary string that you might be able to collect. We want them to be accurate so that similar files or files that are considered similar by security experts are put together and that, or have a low distance, and that files that are considered very different, perhaps created by entirely different processes, have a high distance or low similarity. Ideally, these techniques should be resistant to attack. In those studies and other literature in the area, we find that one key area has been excluded: fast search and clustering. This has typically not been evaluated as a part of the hash. In this paper, we present that this is a key criteria. The reason for this is that security requires scalable search. We need to be able to very quickly identify, yep, this item is very similar to a sample that might be out of a collection of tens of millions or hundreds of millions of files. We also want to be able to scalably cluster files, and we need to be able to cluster files, millions of files every day. So fast search and fast clustering are key elements. Fast search is the problem of, given a search item, we need to be able to quickly identify the closest items out of a large database or collection of files that we're searching through. The typical way to approach this is to build indexes and using trees to build those indexes. So methods for doing this include KD trees, regression trees, and they use features or coordinates at the nodes. So here we present a KD tree that alternatively uses X and Y features from each data point to separate the space. This works well for low dimensional data, but it has issues once the data is high dimensional. And many security problems have high dimensional data. This is a typical problem. TLSH trees, as presented in this paper, are a type of metric tree. By a metric tree, what we mean is that at each node, we put an item from the data set that we're searching through, and we calculate a distance that's suitable for that node within the tree. So we can put items in the tree that will compare a search item to. At each point in the tree, we calculate the distance, and we do this in a way that will roughly balance the tree. So we select the distances such that half the items in our data set that we're searching through are less than the threshold and half are greater than the threshold. So we're able to achieve a roughly balanced T by iteratively going through and partitioning up the data, selecting appropriate distance measures. Let's use this tree to do a nearest neighbor search. So we have a search item and we're comparing it with the root node, TLSH number 1. We find that the distance between them in this example is 125. So since 125 is less than our threshold at that node, we go left and we'll continue looking in the left subtree. Well, that's a fairly clear heuristic, but now we want to quantify it and turn it into a rigorous approach to search. Well, let's consider the following diagram. We have TLSH1, the node or the item at the root node, and we put it at the center of the diagram. We find that the search item is in the green area. So, and what we find is that all the items in the left subtree are in the yellow and green areas. And we find all the items in the right subtree are in the red area. Then we can apply our intuition to this diagram and identify that all items, that the search item is definitely at least 100 distant from all elements of the right subtree. We can construct a bound. This is mathematically satisfied if we obey the triangle inequality. So using the triangle inequality, we can prove that the distance from the searcher item to all elements of the right subtree is greater than or equal to 100. So this is the method used in vantage point trees. We can continue the search and we can continue applying and identifying bounds. So at this point, we've got to the leaf in a tree. We should search through the items in leaf 3. And now we can continue our search. We might want to look at other nodes. Because of our bounds, we can either backtrack and identify other suitable areas, and we can prove which areas we should not look in, or, so that's the first method mentioned. We can use backtrack to optimally search the tree, or we can just build a forest of trees and achieve approximate nearest neighbor. These methods achieve order log n fast search. So we only have to do the order log n comparisons in our search. Now let's look at these alternative criteria. So SSDeep and SDHash don't have metrics. So what we see is a typical tree that would be constructed if we try and apply this methodology. It creates an unbalanced tree. The reason for this is that the similarity measure goes from 0 to 100. If you achieve a score of 1 to 100, you have some similarity with the file. If you achieve a score of 0, you have no similarity. So what we see is that most of the time, or the vast majority of items will have a score of 0. And throughout the tree, we see that most of the items are in the right subtree. In effect, we create a linked list and we've achieved linear search. It's just not helpful. We now apply that fast search tree to hierarchical agglomerative clustering. And this is the HAC-T clustering algorithm. So normally hierarchical agglomerative clustering is infeasible because the first step is to compare every item with every other item. That's n-squared comparisons. And once we scale up, even this first step is infeasible. The HAC-T clustering algorithm takes as input the n items and a threshold t. The first step is to create a list pair data structure. And what we do is for each item, we put it into the fast search and we identify the closest item. So this uses order n log n comparisons. And what we can have is for every distance between 1 and t, we can have the list of items that are that far apart to the closest item. Then we start the clustering process. Step 2, we've just put every item into a cluster of size 1. Then we go through each distance from 1 to t. We use the list pair data structure. We go through the list of items that are 1 apart and we merge those clusters. Then we go through the list pair for distance 2, 3, up to distance t. And at that point, we've created a whole series of clusters and we know that there's no items that have a distance less than or equal to t that are in separate clusters. So we've achieved hierarchical agglomerative clustering in order n log n steps. At this point, I'll hand over the presentation to Makit Ali. Thank you.
Hi, so my name is Makit Ali, and I will be talking more about the experimental evaluation and the results. So firstly, more about our experimental setup. So we used a 32-core machine that had 128 GB of memory with AMD processor. So the reason that we used a 30-core machine, that some of our algorithms that we compared HAC-T with were parallelized so that we can make the experiments more tractable. Just note that the HAC-T itself runs on a single core and does not need 128 GB memory. It runs fine with just 16 GB or 32 GB. So more about the data source that we used. So our data was sourced from VirusTotal data feed, and we kind of restricted our attention to PE files in this study. And from the VirusTotal data feed, we extracted the scan results. It has a bunch of major antivirus vendors information there, but we focused on 5 major antivirus vendors, and these are Kaspersky, Microsoft, Symantec, Sophos, and McAfee. We didn't include trend micro labels in there because we wanted to be like vendor agnostic. So the scan results themselves include labels, and these labels refer to whether the file was detected by the respective AV vendor or not. So we kind of use that information when we do our clustering analysis to like determine the clustering quality. More on that later on. And lastly, we compute the TLSH hash of the PE file. So you can think of it like that. The TLS hash will be the feature that will feed in to the clustering algorithm. So moving on to evaluation methodology. So we wanted to measure clustering quality on large number of samples. So we are talking about millions of samples. So we evaluated up to 10 million. So there are some challenges involved when we want to evaluate cluster quality when we have such a large sample space. So we couldn't make use of other cluster quality measures like sellout coefficient because they don't scale that well. The sellout coefficient itself scales quadratically with increasing sample sizes. So one could use that for like 100,000 samples, but for samples in the millions, it's not a good choice. So we focus our attention to purity. So purity is like easy to explain. So it varies from 0 to 1. 0 is for worst cluster quality, 1 is for the best cluster quality. And the way to calculate is you look at the labels, you look at the majority class label within each cluster, and you sum them up over all the clusters, and then you divide that by the total number of samples. So purity score scales linearly. So that's the good news because we are dealing with tens of millions of samples. So we want cluster quality metric which scales linearly. So comparison with other well-known clustering methods. So we kind of compared with k-means, k-medoid, Clarence, which is also a k-medoid-based algorithm, and also with dbScan, which is a density-based clustering algorithm. So what we found was that these clustering algorithms, they were either not scalable or they did not produce good cluster quality, which could be useful for security analysts. So we found that k-means and k-medoid based methods in general, they did not produce good cluster quality. On the other hand, dbScan, it did produce good quality clusters, but it doesn't scale as well. So we want a solution that kind of scales well with increasing sample sizes, but at the same time can give us good cluster quality. So just a little bit more about these other techniques that we compared with. So first up, k-means. We could not use standard k-means because we are dealing with TLS hashes, and the distance between TLS hashes is computed by TLS distance, which is different than the Euclidean distance, which is used in the k-means. So we kind of adapted k-means for our purpose. So it's kind of an approximation to k-means. So we converted each TLS hash digest to 70 character vector, and then we calculate the mean of the vectors, and we call that M here. So then the second step, we we actually find the TLS hash digest, which is closest to M, and we make use of TLS distance in the second step. So in this way we find D. So this D is actually the means that we use in the k-means algorithm, and the rest of the algorithm is as such. So note that because convergence is not guaranteed, because we are not making use of Euclidean base distance, so we have a max iterations parameter. We set that to 100. So after 100 iterations, we terminate. So some other methods we also compared with the simple k-midroid. So that works by computing midroids based on the average TLS distance computed for each sample. And then you look at the sample which has the minimum average TLS distance, and we assign that as the midroid. And then the algorithm proceeds. So some other techniques that we compared with are Clarence. That's another k-midroid based algorithm. Actually, it's a graph-based method where each node is actually a set of midroids, and then you proceed by selecting a neighbor randomly. And if so happens that the neighbor gives you a better solution, then you go with that neighbor. Otherwise, you keep on searching, and you're only allowed to make a threshold number of selections. And if you couldn't find a better neighbor within the threshold number of selections, then you terminate. And dbScan is like a well-known clustering algorithm. So we also compare with that. So the conclusion was that, as I'll discuss tables also, the k-means k-midroid approaches produce poor cluster quality, while dbScan produces good cluster quality but has scalability issues. So this is the table. So we kind of varied k and n, and we kind of saw that this is still out coefficient, so it doesn't produce good values. So it's seeing values from 0.05 to 0.15. So it doesn't produce good cluster quality. And compare that with table 2, where we have dbScan with various parameter choices. So it produces far better cluster quality, as Tlsh is goes as high as 0.92. So there are some trade-offs involved here also, like for if increasing epsilon, you can cluster more points or samples, but your cluster quality decreases. So you have to make some adjustment there. So how that compares with HAC-T. So we restrict our sample to 10,000 for this comparison, and so that we can use sellout. So if you compare that with dbScan, so the sellout is comparable, but it beats dbScan in terms of runtime a lot. So dbScan is like giving us close to 100 seconds, but here it's like between 1 and 2 seconds. So HAC-T is much more scalable. Next, we discuss scaling it to tens of millions of samples. So here in table 4, we vary n number of samples between 1 million and 10 million. And we see that it scales pretty well. It can scale it can cluster 1 million samples in like under 10 minutes, and then 5 million under 1 hour, and 10 million a little bit more than 2 hours. And here we made the choice T as 50, which is kind of made as a compromise to kind of account for both the trade-offs. Like we want to cluster as many samples as possible, but we still want to have good cluster quality. So in the last table that I present, we have 5 major antivirus vendors, and I calculate the purity score, and it's presented for T is equal to 50, and number of samples are 10 million, and we see a very good range between 0.97 and 0.98. So we conclude that HAC-T is pretty scalable, it can scale to 10 million samples and possibly much more than 10 million. It can scale to tens of millions, and we have shown that it has good cluster quality. And unlike K, means K-medoid, it does not need K as the input parameter. So thank you very much. This work was based on Tlsh, which is open source library. If you have any questions, you can shoot us an email.